Now let us see another speed control method, that is frequency control method. Okay, we know that our synchronous speed equal to ns equal to 120 f by p. Okay, so we are going to change the frequency so that we can change the speed of the machine. Okay, so here I can decrease the frequency so that the speed of the synchronous speed will reduce, so that our speed of the rotor will reduce, and I can increase the frequency so that our speed of the synchronous speed will reduce, synchronous speed will increase, and our rotor speed will increase. So that here I can get the speed as below rated by reducing the frequency, and above rated by increasing the frequency. Okay, in voltage control method I can only reduce the speed by reducing the voltage. That is a narrow range of operation, narrow range of application. Okay, only reduced speed can be obtained in voltage control method, but here wide range of speed can be applied. Okay, wide range of speed variation can be obtained. I think I can say that below rated can be obtained and above rated can be obtained. Okay, so now let us see what is happening when I am going to reduce the frequency of the system. Okay, we know that our flux is proportional to V by F from EMF equation. Okay, so as we are going to reduce the frequency here, what will happen to the flux? That will increase. Okay, and we know that our BH curve, okay, it is like this. It is already near to saturation. This is B curve and this is our current curve H. Okay, so on H I can say it is my magnetizing current. Okay, so for a small change in reduction in frequency, our flux will go beyond like this. That means for a small change in frequency, our flux will be like this. It is almost near to saturation. That means our flux will need more magnetizing current from the supply. Okay, initially it was here, but small change in reduction in frequency increases the flux to here. This is phi 1, this is phi. Okay, that means I am going to need more magnetizing current. Okay, that means our no load power factor pi naught will be reduced. Power factor pi naught will be reduced, which reduces our input power factor pi 1. That means for a reduction, for only reducing frequency, we are going to increase the flux needed by the machine. That means we are going to increase the demand of magnetizing current from the source. That reduces our power factor, no load power factor. This is no load power factor, and this is our input power factor. Okay, that means we are reducing the no load power factor and input power factor by reducing the frequency. So for that, what we are going to do is we need to make our flux constant. How can we make this constant? By keeping B by F ratio constant. So by changing the voltage with respect to change in frequency, we can make it constant, so that our flux will be constant, so that there will be no need of our high magnetizing current, which reduces power factor. So by reducing voltage in addition to our frequency, we can keep the flux constant. And we know that the maximum torque and starting torque of the induction machine, which are proportional to our maximum torque proportional to V by F whole square, you know that, and our starting torque is proportional to V by F 1 by F into V by F whole square. So for V by F is V by F constant, our maximum torque will be constant. And what happens to starting torque for a V by F constant? That is, our starting torque is inversely proportional to frequency. As frequency reduces, starting torque will increase. Now let us see the torque slip characteristics for this. Okay. So the torque slip characteristics will be like this. Okay, for frequency F, this will be the torque slip characteristics. Okay, for reduction in frequency, this is my maximum torque. Maximum torque is constant. So this is my starting torque. Okay, this is for supply frequency. Now I am going to reduce the supply frequency to F1, which is less than F. Okay, so this will be the new torque slip characteristics for frequency F1. Okay, and speed will be ns1. Okay, and for F2, which is more or less than F. Okay, F2 is more or less compared to F. These are the torque slip characteristics, and you know that the maximum torque is constant, and all these torque slip characteristics meeting the load at one point. Okay, I can say this is the constant torque drive. I can say it is constant torque drive. I am getting constant torque to load, so that I can make it as constant torque drive. That means V by F is equal to constant is a constant torque drive. Okay, so now let us see what is happening for above rated. Okay, that means if I am going to increase the frequency, so what is happening? Now let us see. And under running condition, for V by F equal to constant. Okay, under running condition, what is the torque expression? Torque equal to 180 by 2 pi ns. Okay, under running condition, torque equal to 180 by 2 pi ns into S V1 square by R2. This was the torque expression. So you can write slip equal to ns minus nr by ns. You know that. Okay, so I am going to substitute this. Okay, that will become 180 by 2 pi ns into ns minus nr by ns into s is replaced with that expression. So this is the new expression. Now let us see what are the frequency terms here. That will be here this is one frequency term, this is one frequency term. Okay, ns is a frequency term, so that I am going to consider v1 by f whole square, can I write like this, into ns minus nr. These are the proportionalities here. Okay, our torque is proportional to v1 square by ns f into f square into ns minus nr. Now in order to make our torque equal to constant, as our v by f is already constant, okay, to make our torque to the load constant, as v by f is already constant, so our ns minus nr should be constant. That means this is nothing but slip speed, right? Ns minus nr is slip speed. That means the slip speed should be constant for a v by f control. That means for a v by f is equal to constant, our slip speed should be constant. Okay, so this is one important expression. That means for a torque slip characteristics, if you are going to draw, okay, here this was the first torque slip characteristics for f, this will be second for f1, this will be third for f2, f3, right? T max is constant. See T max. Now you can see here, if this is my load torque which is constant, okay, so our nr will be like this. This is my nr1, this will be nr2. You can see this is ns2, ns1, ns. Okay, here the ns and nr difference is nothing but slip speed, right? So this is slip speed for f, this is slip speed for f1, this is slip speed for f2. Okay, you know that f2 is less than f1 is less than f. Okay, that means this slip speed should be equal and it is constant. That is the idea. This slip speed should be constant for the given v by f equal to constant. Okay, now let us see what is happening for if I increase the frequency. Now let us try to understand what happens if increase in frequency. So we are going to increase the frequency here. Okay, that increases the speed of the machine. This is nothing but above rated operation, above rated control, above rated speed control. Okay, so here as we are increasing the frequency, there is no increase in the flex, so that there is a reduction in flex. That means there is no need of extra magnetizing current. That means we are going to reduce the required magnetizing current. That means there is no problem with power factor. So this is one advantage. So as there is no problem with magnetic field, we don't need to change the supply voltage. As we had a problem with reduction in frequency, so that our flex will be increased, we had to reduce voltage such that V by F ratio should be constant for reduction in frequency. Now there is no problem of flex, so that we don't need to change the voltage. Okay, so that we don't need to maintain the V by F ratio constant. We are not maintaining V by F ratio constant. Now what is happening to our torque, maximum torque and starting torque now? As maximum torque is V by F ratio, okay, so V by F whole square, that is dependent on F square. T max is inversely proportional to F square. As V is constant here, T max is inversely proportional to F square. As we are going to increase the frequency, that our maximum torque will reduce. For increasing frequency, our maximum torque will reduce. And what is happening to our starting torque? Here, as V by F ratio is not constant, our starting torque is inversely proportional to frequency, and we are going to increase the frequency so that our starting torque is reduced. So for increasing frequency, our starting torque is also reduced. Now let us see the torque slip characteristics for increasing frequency. Okay, so initially it was F, now I am increasing to F1 and F2. Okay, F1 is greater than F2 is greater than F. Okay, so for F, this is the torque slip characteristics. For F1, you know that the starting torque has been reduced from here to here, and maximum torque is reduced from here to here. Okay, so this is the torque slip characteristics for increased frequency, and this is further increased frequency. Okay, now you can see for a low torque, let me consider this is, so let me take a problem for V by F equal to constant. Okay, so I am going to take a 400 volts 50 H supply, has synchronous speed as 1000 rpm and running speed NR as 950 rpm. Okay, now I am going to change the voltage and frequency such that V by F equal to constant. Okay, so that will be 320 volts 40 H, and you can see that V1 by F1 should be equal to V2 by F2. For V by F ratio should be constant. You can verify here, that is 400 by 50 should be equal to 320 by 40. You can see 5 H 4 H. Okay, this is what V by F equal to constant means. Okay, these voltage and frequency ratio should be constant. So I can consider it as from the given expression. So these are the given data. You need to find the speed of the rotor NR2 if torque is constant. So this is the given question. Okay, so let us verify V by F is equal to constant or not. Okay, we can make it as 400 by 50 equal to 320 by 40. So I can get as 8, which is constant. Okay, that means V by F ratio is constant here. Okay, that is nothing but constant torque. Now we have the expression for torque equal to Ns minus Nr into V by F whole square. So as V by F is constant, we can write it as torque is constant. So I can write Ns1 minus Ns minus Nr1 into V1 by F1 whole square equal to Ns minus Nr2 whole square into V2 by F2 whole square. Okay, so you can substitute the values here so that you can get the answer. So Ns is 1000 and Nr1 is given 950 rpm into V by F is 8 whole square is equal to ns is 1000, nr2 is to be find, and v by f is 8 whole square. So you can cancel out here. Okay, so nr will be equal to 50 plus, sorry, ns2 is something different, right? ns2, because the frequency is changed, ns2 will be 120 into f2 by p. Okay, p can be given by ns1, which is equal to 1000 here, that is 120 into 50 by number of poles equal to 1000, that will become p equal to 6 from given first ns1. Okay, so number of poles are 6 here, so you can substitute in ns2, so that 120 into 40 by 6, that will become, what is ns2 here, 6 2 ja, that is 800. So this is 800 here, the speed is 800. Okay, and v by f ratio are constant. Okay, so you can find that nr equal to 750 rpm. Okay, this is for v by f ratio is constant. As I have reduced the voltage and frequency such that v by f ratio is constant, our speed has been reduced from 950 to 750. So this is nothing but speed controlled by frequency. Now let us see another. So now let us try to understand the torque slip characteristics for increase in frequency. Okay, as we are not making v by f ratio not constant, it is not constant. Okay, now let us see here, as maximum torque is reducing as we are increasing the frequency. Okay, f2 is greater than f1 is greater than f1. For f, this is the starting torque and this is the maximum torque, and for f1, which is greater than f, our starting torque has been reduced and maximum torque has been reduced. Okay, and for f2, which is greater than f1, our starting torque has further reduced and maximum torque has further reduced. And you can see the speed locus, that is, this is nr, this is nr1, this will be nr2. Okay, the curve will be like this. Initially the curve was a straight line, that means as they all are constant. Okay, it was for v by f is equal to constant, the curve was like this. Okay, now it is like this. That means I am going to summarize both the, for v by f the torque is constant, for v by f is not constant, this is like this. That is, this is for v by f equal to constant, this is v by f is equal to not constant. Okay, this is at rated speed, n rated. Okay, this is above rated, this is below rated. Okay, so this is nothing but similar to our Watt-Leonard method of speed control in DC machine, right? This is constant power drive as P inversely proportional to speed. Okay, this is constant torque drive. Okay, this, by changing the frequency, by reducing the frequency, we can get the below rated speed. By increasing the frequency, we can get the above rated speed. And it is v by f ratio is constant for this period below rated, and v by f ratio is not constant for above rated. So this is about frequency control of speed control of induction motor. Okay, thank you.